All right, so let's read this together. I have, for 1.3, we're going to report with accuracy. So, one thing I want to point out is this essential question. How do I use significant digits when reporting results to calculations involving measurements? Okay. So let's read this. It says, numbers are values without units. They can be used to compute or describe measurements. Quantities are real word values that represent specific amounts. For instance, 15 is a number, right? But 15 grams is a quantity. So a lot of times in math, we're going to be measuring something here. So we're almost always going to be measuring something in math. That's what we use math for. We measure something. And then accuracy. So let's talk about what the difference is between precision and accuracy. Okay. So precision is the level of detail of the measurement, determined by the smallest unit or fraction of a unit that can be measured. Now, accuracy is the closeness of a given measurement or value to the actual measurement or value. And it sounds like kind of the same thing, but they're believe me, they're actually a little different. Okay? So, let's unpack this and try to figure out the smaller unit, and then also we want to figure out a more precise measurement. So give me 1 second. I just want to pull up my thing here. So when we talk about a smaller unit, we have the measurement of 4 grams or 4.3 grams. So what we're supposed to do is we're supposed to complete the table and choose the more precise measurement. So when they say more precise, let's work out of the order. Which one is more precise, do you guys think? 4 grams or 4.3 grams? Mm-hmm. 4.3. It's a little bit after lunch. I had to eat a snack. Now, what's the smallest unit that we're measuring, though? 0.1 grams. Okay. Can you guys see that color okay in the back? Mm-hmm. Okay, let's look at these. Which one's more precise? 5.71 or 5.7? Mm-hmm. 5.71 ounces, right? Now, what's the smallest unit? Well, it's to the 1,000 or 100ths, right? So it's this. That's the smallest I could possibly measure. Do you understand that the smallest unit is the smallest measurement I can get of the more precise measurement? 4.2 meters or 422 centimeters? Which is more precise? Now, that's a trick question. $422 centimeters is equal to 4.22 meters. This is tenths. What's a centimeter? Hundredths, right? So this one would be 1 centimeter, which is 1/100th of a meter. So 422 is the more precise. Okay, 7 feet 2 inches or 7.2 inches? Which one's more precise? Well, here the smallest unit is an inch. Here I have 1/10 of an inch. So I'm going to say 0.1 inches, and therefore 7.2 is a more precise measurement. And I think when we talk about precision, let's look at the images of a meter stick. So if I zoom in on this bad boy, and this is not the best illustration, but this is 1/10 of a meter. This is 2/10 of a meter. This is 2/100ths of a meter. And then there's little lines that are blurred out that are 1/1000th. Each little line represents 1/1000th of a meter. So when we talk about precise, we're talking about measurements that are closer and closer and more precise, smaller and smaller measurements. Okay? That's what they're referring to. So let's do this same thing with the scale. So it says that Eric is a lab technician. Every week he needs to test the scales in the lab to make sure they are accurate. He uses a standard mass of 8 kilograms, or not 8 kilograms, 8 grams, and gets the following results. So he's trying to figure out which ones are the most accurate. So which ones are the closest to 8 meters? Well, the measurement for which one is the most precise? Let's start there. Scale 1, scale 2, or scale 3? Which one is the most precise?
Scale 2.
Well, this one we have 2 decimal places. This one we have 1 decimal place. Here we have 3 decimal places. Right? So this is the smallest measurement is 0.01 on this one. The smallest measurement on this is 0.1. And the smallest measurement you can get on this one is 0.001 grams. I suppose we could toss a 0 in the front. So those are the smallest measurement. So when you think of it that way, which one has the most precise measurement? Yeah, scale 3. All right, now because it measures to the nearest 0.001, 1,000th, which is smaller than the smallest unit of the other 2 scales. But now we want to figure out which one is the most accurate. So because we want to figure out which one is the most accurate, we got to do a little bit of math. So we're going to take 8. What was the measurement on scale 1? Wasn't it 8.02? And so when you subtract those and you get the absolute value of that, right, this is going to be negative 0.02, but when you take the absolute value of that, it's just going to be 0.02. For this one, scale 2, the measurement was 7.9. That's actually going to be 0.1. And when you plug in 8.029, then the difference between those, and you put the absolute value bracket on it, is 0.029. Okay? Does that make sense? I shouldn't record videos right after lunch. I'm snacking, drinking a pop, stretching. All right. So we're almost done. Complete the statement for the measurement 1 is 8.02 grams, and the most accurate because 0.02 is less than 0.029 is less than 0.1. So when we want to find out something, which one is the most accurate, this one is the most accurate because it has the lowest difference than what the scale is supposed to be. In other words, the weight that they have a weight that goes on there. It weighs 8.000 grams. And so what we want to do is when we weigh them on the scale, we see that there are differences. And remember, accurate means that we want the one that is closest to the actual measurement. So closest, oops, I misspelled closest. Eraser. Closest to the actual measurement. Okay. Any questions on that one? So real quick, let's do one more reflection on this. It says, given two measurements of the same quantity, is it possible that the more precise measurement is not accurate? And why do you think? Well, now look at this. Which one of these was the most precise? Yeah, scale 3 was, right? This is the most precise. This was the most precise. Why? Because it measured this, right? But which one was the most accurate? This was the most accurate because it was closest to the original value. Okay? So we just need to put that in our own words. So we would say, and so let's reread the question. It's the given two measurements are the same quantity. Is it possible that the more precise measurement is not the most accurate? So I would say something along the lines of, yes, it's possible. Scale 3 was the most precise, but scale 1 was the most accurate. Well, if you look at the answer in the back of the book, it'll give you a lot of reasons why that's the case, but it could be the person, it could be the device, it could be a lot of things, okay? But that's what it is. Let's move on to the next one. So I'm basically just going to kind of read this stuff. So let me move my face out of the way. It says find the length of the width of the book cover. I'm sorry. It says find. It doesn't say find. It says the length and the width of the book cover are 28.3 meters and 21. I'm sorry, not meters, centimeters and 21 centimeters respectively. Find the range of the values of the actual length and width of the book. So the minimum length, and I should probably read the question above. It says calculate the minimum and maximum possible areas round to the nearest square centimeter. So when we look at this, if I say centimeter, right? So 1 centimeter, right? Well, what's the lowest that I'm measuring? I'm measuring to the 10th, right? So let's think about this. My measurement is 0.1. I'm measuring to the 10th. So now I got to decide, am I closer to 0.01 or 0.02? There's something that lives in between here. Well, what lives in between here is 0.15. And where did I get that from? Well, these are the same things, 0.10 and 0.20, and 1.5 is right in the middle. So the middle of this measurement of 0.1 centimeters is actually 0.05 centimeters. So I could be a halfway off, or I could be halfway. And you want to, if I have a, let me see if I can get a pretty good image. I wish the textbook had some images of this. Meter stick precise or precision. This is a good one right here. So we'll just copy this image. So I want you guys, I want you guys to kind of see what I'm talking about here. I'm going to put this up here and then I'll move it away in a second. So when they say 28.3, what they're really doing is they're saying, okay, each one of these little lines is 0.1 centimeter, right? So if I take this, oops, if I make this really big, like really, really big, and like really zoom in on this, whoops. That little line right there is 0.1 centimeters, right? But I could be, am I closer to here or am I closer to here? And what's the difference? Well, I could be, that's basically plus or minus 0.05, right? I could be halfway in between. I could be halfway over, or I could be halfway over here, depending on how you measure it. So when we go to do all this math, I have to consider the next decimal space, and I have to consider this plus or minus 0.5. So to find the minimum length, I'm just going to take this length of 28.3, and then I'm going to subtract 0.05 from it, or to find the maximum length, I'm going to add 0.05. So I've got a measurement here. This is 28 centimeters. Then I've got 1, 2, 3. Okay? And that's the 0.3. And I'm trying to figure out, well, what's my error range? Well, I could be a little bit over here on this side, or it could be a little bit over here on this side. This side would be 0.05 subtracted, right? This side would be a positive 0.05, roughly. In other words, if I'm measuring something, it doesn't matter what I'm measuring, But if I'm measuring something, anything, whatever it is, I gotta be careful because it might not be precise. Like it could be a little bit this way, it could be a little bit this way. I won't know until I get over here. I won't know until I get over here. So we're going to assume that it's somewhere in between. That in between point is going to be my negative 0.5 or my plus 0.5. So when we do the math on that, I get 28.25 or I get 28.35. Now, for the minimum length on the other one, I'm going to do the exact same thing. I'm going to either subtract 0.5 or I'm going to add 0.5. Now, why is it 0.5? Because 21 is the same as 21.0 or whatever, but it's the same thing. I can have 20 centimeters here. I can have 21 centimeters here, and I can have 22 centimeters here. So when I go to measure this, whatever this object is, this object may not necessarily measure up right at 21. It might go a little bit over, it might be a little bit less. I probably won't count it as 20 unless it's over here. And keep in mind, Mr. Adams is drawing this so it looks like we're zooming really far in. Right? We're zooming really far in, but it might be a little over, it might be a little less. So in this case, well, what is a little less? Well, in this case, a little less would be minus 0.5, and over here would be plus 0.5. So you're going to plus or minus 5 to the next decimal place, basically, is the best way to word that. Okay? Oops. Any questions on that? So now that I've got all that done, I find that the maximum area is the product of those two numbers. So the maximum area is going to be the maximum length times the maximum width. So I'm going to have my maximum length, which is 28, this is the max here, times the maximum, oh, I'm sorry, I'm saying maximum, but that's not, let me erase this so I can do this a little better so it makes more sense. So the minimum, let me get some specific colors. Let's do blue. So if I want to find the minimum area, dang it, I wanted this blue. If I want to find the minimum area, I'm going to take the minimum length. What's the minimum length? The minimum length over here is 28.25. That's this right here. Multiply it by the minimum width. Because remember that the area is equal to the length times the width. Now, if I want to do the maximum width, let's pick a different color. We'll do orange. Okay. To find the maximum area, it's still the same formula. The area of a rectangle is equal to the length times the width. I'm going to take the maximum length. This is the maximum length right here. And I'm going to multiply it by the maximum width. This is the maximum width. And so then I'm going to say that my area lives between the minimum area and the maximum area. So this is the minimum area, this is the maximum area. Okay? That's a lot for one example problem, don't you think? All right. Well, I'll give you a second to digest that.